Okay, so thanks for the invitation, and I met Eddie 8 years ago in Kassel because we were thinking maybe working together on ConED, but unfortunately he had other plans, so we had it to do on our own. Right now I would like to speak about our product ConED, which we will market by the second half of this year. And what is maybe special about this presentation, actually I'm an engineer and started developing this software for engineers for conceptual design together with computer developers and designers as a multidisciplinary work. Yeah, shortly or briefly about our company. Right now we are 17 people, 15 employees and 2 stakeholders, and we work, let's say, mostly on the design consultancy market for building structures, different kind of materials, concrete, timber and so on. Yeah, how came that we started working or developing the software ConED? It started out that we said, okay, the market, the consultancy market is quite competitive and we have to do something about this instead of just saying, okay, time goes by and we work harder and harder and harder like other offices. We have to develop good ideas to cope with the new situation with more computers and so on, numerical computation and everything else. So this is actually the idea or the core of my talk, that I try to give you the idea and to give you a picture how ConED will influence in the future the work of structural engineers, and what is special about ConED maybe in terms of being a software product, having some kind as a basis engineering knowledge combined with the geometrical computations. How started everything out? Yeah, first there was this idea for the software, then I will say a couple of words about that. The next thing I would like to speak about, what is ConED. I assume that you're probably not familiar with structural engineering, so I just try to give you a brief idea about the task for an engineer designing a structural concept that brings down all the loads to the ground based on an architectural design. Third part I would like to speak about is the core of ConED, the load transfer. The load transfer computation are basically used for the engineer uses it for figuring out what kind of concepts he can develop that have a secure and robust load transfer that brings all the loads through the different structural systems and elements down to the ground. And last but not least, we started out with the idea pretty early and worked on ConED since 2003, so almost 10 years from today. What we actually learned on our journey from the very start until, let's say, a robust software application that we will ship by September this year. Okay, let's start with the first issue. Actually, our experience, 75 years in engineering, and our ordinary style of working was not sufficient to cope with the current situation. So we considered that we really have to change something, especially we are not a very large engineering company, so we don't have the manpower like larger consultancies. We have to work more efficiently. Second, I mentioned already this issue too, that the market, we're on a regional market, it's quite competitive, and the price is usually the point where you get the project or not. Yeah, so you can't really considers other aspects of convincing the client to give you the project except of price and for, of course, the quality you always have to deliver. Yeah. How started everything off? In 1994, I was 20 years old. I used to walk a lot with my father after work, and we talked about actually what are the major mistakes engineers do in practice when they have time pressure and so on. And he mentioned a couple of times, the problem is really to bring the actions, the loads through the structure into the ground without making any mistakes. And right now this is still paper-based, so you don't have any kind of computer aid. Yeah, so going with this idea, I started 2000 working out the theoretical basis with my PhD, which ended 2004, and then 2002 we started developing the software in Dresden with a couple of guys, 3 persons, and yeah, gave our best, but by the way, a lot of things still happened later on. 2006, I made a major mistake. I had a software developer from Pakistan, which I knew from my studies in computational logic, and he said, "Oh, and if we don't manage to get it in time, we just rent an office in Pakistan, hire 5 to 6 Pakistani people, developers, and then everything will turn out in 1 year. You are ready, you are a rich man, take your bathing clothes, sun cream, and everything is fine." So, up to now everything was okay, but then I said, okay, let's do it and give it a try. And I figured out that it's really a major problem providing the quality if somebody else working externally in another language. You have for sure the management tool, or the tools for version management and so on, but you have to, let's say, have to have 2 or 3 iteration cycles to provide the quality you need to get shipping software. Then I decided 2008 only to develop in Kassel, and right now we are 4 persons that develop the software. And finally this year, and so it fits perfectly to this talk today, I'm glad to say that we are finishing, we are in the final testing phase, and we will sell the software and this year and start marketing and so on and so on. Yeah, to give you a brief idea about what structural engineers do in their practice, here is an architectural design, it's a concept. This was actually planned to become our new office building. We are going to move in. And as you see, usually you have, these are different views from different sides. Usually you have a special layout. Yeah, and some kind of special constraints, like here, no load-bearing elements are allowed, and maybe some other facade constraints, like on the right-hand side, that no, let's say, solid walls or other elements are allowed at the window panels. What the engineer usually does is he takes this, let's say, this idea and tries first to get a grip on the design, like how can I develop or design a structural concept that the structure is stable, is not turning over, and so on. So for this small example here, he is figuring out, okay, where do I need columns, frames, and so on, and he has to ensure that by his design all the loads flow through the, let's say, top or the application point of the actions into the ground. Yeah, the engineer usually feels very strong working in a creative way, so he doesn't like let's say yesterday evening we had this discussion, like case-based reasoning methods, where he gets presented an idea and says, okay, I just adjust it a little bit and then everything is fine. This is for the engineer a very creative task, and therefore the software needs to consider this also very deeply in the design. Probably you're familiar with the usually CAD systems that are around the market. What is actually the difference between ConED, the conceptual engineering editor, and the ordinary CAD systems? As I said, it's from engineers for engineers. It's really driven by the task at hand. For the one task, designing a structural concept. So we carried out a lot of design studies, analyzed design protocols and so on with psychological techniques in order to figure out what is the conceptual model. On the one hand side, we know from our work, but also for a general, let's say, engineering community, because we would like to sell the software to a lot of engineers. We don't want to just work with the software on our own. And what is also very important, that the work is usually, I would say, money and time driven, that if the engineer doesn't get really precisely, immediately support by the new software, he doesn't use it. Yeah, so this is really something special in our industry, that if you give a new tool to the user, to the end user, he doesn't have time to test it and to get familiar with it. He says, okay, I would like to work like, it's like with Apple, he says, okay, give it to me and I work with it. If it's not working, I give it back to you, I return it and give me the money back. So, therefore, we really tried to focus only on the conceptual and preliminary design of building structures, multi-story buildings, and the core, I will talk later on a little bit in detail about this, is the load transfer. Then, and this is very important, I also told you it must be very simple to use, so usability, GUI design for an interactive application is crucial. So, and what's special, at least in our design community, we said, okay, we don't want to develop a feature-driven application. We would like to develop a task-driven application that the user just can make the task, designing a structural concept more convenient, and that's it. Maybe if one conclude everything, you could say it's a preprocessor for engineering designs using different models. Yeah, what are the models we work with? The structural concept, in order to later on describe the load transfer, is made of a number of structural elements. Here, let's say this is a rendering, just showing the structural concept or structure an engineer has in mind. A number of structural elements, columns, girders, diagonals, flaps, walls, and so on. Then grouping into systems with their interactions. So usually the engineer does not make a 3D complete numerical computation, but he decomposes the overall structural concept into subsystems and elements, computes the behavior of the elements independently, and then he composes it into an overall solution. Then, the structural concept, as I said, is structured by the load relations. I will later on talk about this between the elements and systems. And the load relations describe the force distribution over all elements. What means that, for instance, if you have like here a column and a diagonal, and this is a frame, how much load flows from this from this column into this diagonal and goes over this trusswork here back into the massive walls. Then for sure, this is a very important task in our domain. You have here this kind of geometrical model, but then you have to abstract this geometrical 3D model automatically into a lower D model in order to compute the internal forces and so on. Like a slab is not a 3D volumetric object, but it has a surface with a parameter thickness and then boundary conditions and so on. So this is in our software, a very complex task in order to get one dimension lower for providing the input for the computational software packages to compute then all the different elements and structural systems. Yeah. Then we have the computational finite element model. This, I said external because ordinarily it's like every engineer got his own computation package. It's like the second heart, and he will never change to a new structural computation package because it's just too risky, because if something is not working, he doesn't know the inside, he doesn't know the theory which is implemented. So we decided, this was a core decision at the beginning, that we will really just develop a preprocessor for external client-side software, and not to do it on ourselves, because this computation packages are around. Yeah, and here's a complete one, but as I said, usually the engineer starts every story, slab, or maybe the roof first, then the support actions, and goes through the building story by story, and applies the loads from the top to the next story level and so on until he reaches the ground. Yeah, what are the very or the most decisive design requirements for the software? Actual usability. So as I said, the engineer would like to use it right away. Then plan-based working means the engineer takes the architectural layouts from the architect, or the architectural layouts, puts on top a transparent paper, and then works on this in order with pencils to figure out where are columns, which column is supported by another, and so on, in order to determine the load transfer. And at least the automatic load transfer, that right now engineers do number crunching in their head, so if they're not very concentrated and relaxed, they make a lot of mistakes. So they are very glad to get a support that they don't have to do it themselves any longer. They can just use ConED. Yeah, just what is the ordinary work of an engineer? He got this kind of white paper. No, not really, but almost. And uses the architectural plan, where the layout with the rooms and the plan by the architect, the planned building elements are situated and depicted. What he does now is that he really takes step by step color pencils and develops a structural concept by the given geometry. Yeah, for instance, like blue is a beam, red are columns, and here, for instance, he says, okay, this is a slab. This span length is too large. I need an additional beam here, which has to be placed or supported by something. I put a column here, and on the other side, okay, there's nothing, maybe also a beam, and the beam goes then to two other columns here in the facade, and so on. And this he does step by step, and the problem is when the engineer or the architect says by the end, oh, maybe I move the column to another position, I have a problem. So engineers don't like that somebody changes later on the overall structure. But with ConED, this is now possible because everything is computed automatically or not by hand again. So the propagation of the load values over the entire load structure, which is basically a graph, is done not any longer by hand. Yeah, this is just to give you an idea what engineers do when they work creatively. So everybody gets another notion of creativity, but for engineers, this is what they like, because on the other hand, they often just use computers to compute columns or whatever and input data and check if the reinforcement is sufficient. Here they really have the feeling to do something creative. Yeah, at the end I will also, maybe if the time allows, I will show a short movie about ConED, but here you have the GUI, which is what important is that this is the drawing pane view where you directly manipulate the geometrical object, so you have a very high user interaction. Then on the left side here you have some kind of object tree, and here below you have a property dialog which we developed ourselves before Franz is the development environment we use. Also brought out shipped a property dialog, which is dynamic in the sense that if you change something here, you right away it's displayed here, and on the other way around, if you change something here, something is also changed here. Then you have also here a message window, and the idea is that the task or the user really can work in the ordinary way of life, ordinary way he's used to, by just working with the mouse instead of a pencil. Yeah, this is the idea actually. And then there's nothing special about it's like a cut system, but not so many icons, because we thought it's not feature driven, but in the end it always turns out if you don't start very slim with a very slim solution, you always widen up your self-set-up requirements in order to have one more nice feature. But I will say something more about this later. Yeah, as you can see already here, the engineer sees again, oh, there is a beam supported by columns and so on, but the computer doesn't know something about columns, about when is something supporting something else, which kind of area intersections are allowed in order to support something. Yeah, this is all, let's say, described by the knowledge implemented in ConED. Yeah, here I have a picture, for instance. This is a small building. The engineer would like to know what objects from above load this column, and which other objects support this column in order to compute the loads along the load path for this column, in order to check for the dimensions, the required reinforcement, and so on. And this has to be done for all elements in the structural concept. So basically the idea is that we describe and represent local rules for each element, and the combination allowed with other elements, and then this makes up the combination of all these kind of local constraints make up the overall space of allowable structural concepts. So here just displayed the load transfer graph, or the load transfer of this column. As you see, this column is directly loaded by this slab, and this column again is loaded by elements up above here. And the column also needs some support. The support is this kind of beam here. This beam again is located on this wall or supported by the wall in two columns, and these are again supported by something else, a footing beam here, and piles because the ground were not so good. So the one thing ConED does is computing on a symbolic level the global load transfer graph for each element. On the other hand, what ConED also does is that it zooms up all the load values from above in order to know the force here in this column to design it. And this is here shown in Germany. It's like that, for instance, that you have to compute the load values independent of the occupancies, like self-weight, office occupancy, wind, snow, and so on. So, for example, this column here has maybe 3,000 about kilonewton force and some others, and so he can now consider, okay, in the very beginning the column has to have dimensions of 40 by 40 concrete strengths, and I can design it, and this load is carried up by the next building element, and so on, and this structural concept is working in the initial phase. This is especially important when you're not really sure about the configuration. Usually the engineers have a lot of experience, but if you have nowadays you have more complex buildings, and even the practitioner cannot say, okay, this structural concept works. He needs to have the real values here at hand for the special case in the project in order to determine it works or it works not. And if we jump back to the very beginning, if I had said to the architect, oh, you need a column just over this space between the left-hand side, he would say, okay, then I redesign my complete architectural layout. So this is very important nowadays, that you have this kind of computation power at hand.
May I ask, I thought you said in the beginning that you used external software for these computations, but now you're saying that you do compute this.
So it's like this, that for slabs and for walls, the deep beams, we use external software to compute the internal forces, but the whole load transfer from one element to another and which element supports another, this is completely done in our software.
But it's not, so you call it these other...
We're just calling it for computing the support reactions and so on.
Dynamically, so you get the results back?
Yeah, and then we feed it in our software. What we right now do, we develop our own... Yeah.
You take into account as well for the support forces, wind and season?
Yeah, we also take care of that. So right now we develop our own software or computation package, but the main thing is, and this is really a design requirement, engineers would like to use their computational software. So it's like, it's more hindering if you say, here I give it for free to you, they say, no, thanks, I don't want to have it. Yeah, now I would like to give you an idea how this, or what goes on behind the curtain when ConED computes which element is supported by another element. Here there's the more detailed displayed this kind of layout we already seen before. For ConED it's just like for every computer on geometry, like a beam has a geometry starting point, end point, a breadth, a length, a height, and so on, and a location in 3D. Yeah, and okay, material, maybe concrete, or for instance, masonry would be for walls, so they couldn't. So masonry walls cannot take up tensional forces, and structural types, like as I said, this is a beam. So And yeah, what can we do now? An engineer now would say, okay, I know this is a beam, this beam, here's an area intersection with this column, so this beam should be supported by this column. At least I know beams can only be supported by columns and walls, and this wall here is on the same location, but if I have a column here, this column takes up the load instead of the wall, and so he figures out what element supports other elements. So basically it's pretty easy, I would say. It's just geometrical intersection things and so on, but due to the mass of possible combination and intersections and all that things, you need to put some knowledge into the system in order to solve it. So just to give you a brief idea, you need the allowed geometry intersections, like I mentioned the slide before. Even though some geometric areas intersect, it might be that they're not supporting each other because it's not enough. Yeah? For instance, if they just touch, might not sufficient. Then you know which element types can load each other. Some elements cannot load each other, like a slab cannot be loaded by a beam element. This is not possible. So you can, let's say, reduce the search space a little bit by using this heuristic knowledge. Then ordering is taken into account, as I said earlier. If you have many elements on one geometrical location, some elements have precedence for others. And another point is what I mentioned with the masonry wall. Not every element can take up every kind of forces. Some elements can just take up compression forces, but no tension forces, and so on. And what is also important, that for later the computational, let's say, logic, since you go down with one dimension when you compute the things, for instance, the slab is a 2D numerical problem, you need to reduce also the geometry of the interrelations where the interaction takes place between the elements. Like if I have a column here and a beam here, then you get a point in 3D where this column loads this beam. You don't have an area, but a point. How looks now, let's say, a naive solution? Here just depicted with different colors, different kind of building elements. The gray line shall represent a slab geometry, the blue line beam geometry, a yellow line column geometry from a story above, so a column above the current one, and a green line is a column in the current story. What we do now in our software and let's say in the basis is that we define load relations for each possible path of building elements, like here the column from above with the slab gives a point load relation with a point geometry, and this is only valid if the geometry is overlapping combined with some assertions that have to be valid in order that it's triggered. So the column then would load the slab here. So here it's inside, the area intersects with this kind of slab geometry, and it would be true. Yeah. The next thing is checks column with beam element. You would see, okay, again, load you have a point geometry. Again, check the overlapping geometry, and you see, okay, it's here inside the beam geometry, so it loads also the beam. So you have two possible objects which might be loaded by the column from above. Then again, you have a load relation defined between columns, and again overlapping geometry, but here you see that the assertion that the center of gravity is not located here inside this green rectangle, this one fails. what means that this column loads, the orange column loads not the green column, but the beam element. And last but not least, the beam element is checked against this column, and you see that the beam element loads the green column, since this kind of overlapping geometry function returns validity. Yeah, so this is just to give you the idea how it works. What we have to, or what I have to say is that you have for sure a mass of elements, thousands like, and so on. So what you have to really reduce, let's say, the space of possible elements and possible methods or computations you have to carry out for area intersection and so on, in order to have speed. Runtime speed that is sufficient, that the performance is accepted by the user. Yeah, this was to give you an idea about the core of ConED. Now about, let's say, the developer's view, what ConED makes out of my view, since it's my baby, a little bit unique. Not always as things that are nice, also that we had large drawbacks. 15 many years development. As I said, we started 2002 with it, so it's a really lasting project with a lot of developers. Unfortunately, together 20 developers were working on the project. Some moved, some new came into the team, and this is really a problem when you would like to develop a robust software, because the code base increases and documentation and testing is crucial, but here in the beginning you neglect it a little bit due to the naive thought that you can cope with the complexity. What is not true actually. Roughly 110,000 kilog code bases, mostly geometry and GUI sources. We use the Franz package for GUI development. Yeah, and what is, I would say, a little bit also hindering that some basic functionalities in other language, they're just there, and in ConED you have to do your own work, like with the property dialog, where you don't have off-the-shelf solutions. Yeah, as I mentioned already, we also have some things in C and C++, AutoCAD import, using a library. We have ported the visualization first, also written with the OpenGL interface to Franz, completely rewritten in C because it was not fast enough for larger projects. And in addition, we would like to have only one geometrical model in all different views the user works with. For instance, you have a 3D plastic view, you have a layered view, you have a cross-section, you have a plan view, so that you don't have redundant data. Then polygon clipping is done using a C++ library, GPC, nothing special, and we use some libraries in alphabetical order. In ConED, probably you're all familiar with the most of them. From the, let's say, the developer perspective, it's sometimes quite hard that you have a basic functionality like CL PDF, but in order to print a PDF plan, what we have to provide for our users, you have to do a lot of, also not low level, but let's say medium level code generation in order to have it then solved. Right now, we have started 2-3 years ago making more testing. Now we are writing more test files and with 5 AM, but the problem is that you don't have just for where you have, a lot of mistakes like in Word come from wrong user interaction, wrong user input. So unfortunately we don't have any kind of automatic test framework for testing the GUI. So if somebody knows about something about that one in Lisp, I would appreciate to tell me, because the main thing is that you get a stable and robust solution when people dragging, dropping everything they would like to, and yeah.
Sorry, you have 5 minutes.
Yeah, okay, I'm almost done. Okay, so. The advantages and disadvantages, I think you're always probably familiar with. Small teams, very quick bug fixing cycles, a lot of things are already said. One thing I would like to pronounce is that the expressive power is sometimes, I think, in Lisp not great, but also hindering if many people work on one code basis. For instance, if somebody uses a lot of macros or whatever, it might be very smart, but if 2 or 3 other people have to fix that and have to check or have to add a little bit functionality, it takes 2, 3 times of time in order to do that. Then when I have to speak about mistakes, maybe they are not mistakes, they're just experiences. It's always very dangerous if you have inexperienced programmers. Unfortunately, in Kassel it was not possible to have experienced programmers since there's no Lisp community. Then another thing is you should really start with a slim solution in the beginning, ship it very early, and then add more functionality, and don't be afraid of the market. I've met another guy at the university where we collaborate and they make a game engine, and we just talked about things, and he said, yeah, okay, we're having this feature and this must be more stable and so on, and there's only, if it's your baby, you are always afraid of the market, and don't be afraid, just do it, keep it slim and robust, and then you will see. So this was also a mistake we did. Write language in the wrong city, I already mentioned. Yeah, another failure was if you start with a prototype, you keep always the major faults in your design from the beginning if it's really a core of your software. So you should really spend time figuring out, if you start developing prototype, would you like to go the whole journey down to make a complete software, and then take your time in the beginning. Lessons learned, very slim, as I said. Then another major problem is always if you have a lot of people working in one code. I mean, there are utility functions like vector manipulations and so on. You see 3 times everywhere spread because the people just speak about that it's there. So you really should communicate. Another thing, bugs belong to 1.0. It's like for engineers, something is right or wrong, but bugs, I don't know, if I make a design, there's a bug, the whole story the whole building could fail. So I'm not familiar with bugs, but I go along with this, and we sell the software also with some bugs left. Spend as much time as possible, I already said, and have an eye on documentation and testing. Yeah, so that's it for the moment. We will start selling, and I hope you enjoyed this brief look into the engineering world. Thanks a lot for your attention.
2 minutes for questions.
Well, that box on the left, the basic, is that a free giveaway or?
No, this is cheaper. So we have different versions.
Can you give me an idea of the price points?
So this one will cost 1,000 and this one 2,000.
Do you have any sort of like real-time failure modeling of components? Like, can you get a visualization or if say a particular component fails or is taken away, how it impacts the rest of the component?
So not in this software package, but we had a research project where we developed a module on top for this software for progressive collapse, and there this is covered.
Just in addition to that, what's the kind of computation load for that? Does it take a lot of offline processing, or is it like real time?
No, here it's like processing time, real time. Usually the user moves an element, adds an element or whatever, and then you have to recompute the whole graph or parts of the graph.
And that takes a non-insignificant amount of time, yeah?
Pardon?
Does that take a significant amount of time?
Yeah, for sure.
Hours or minutes or?
Yeah, it depends. We are working, redesigning always the core. If you have now a very large data, it might take, in the beginning it took half an hour and now 10 seconds. Yeah.
I've just one last addition to that, because I was just thinking, you mentioned actually games there. I was thinking, that would there be a possibility of like stripping it down so it's not so academically correct, because you could use it in like a real-time simulation, like a game, so you could have building failures, you know, and then have that animated.
Well, you could, but it's not our field.
Yeah.
I thought of, but yeah, because they have a physical engine and so on. Yeah, right. Mm-hmm.
You started out with the project in order to gain productivity boost. Do you have any idea of the amount of productivity that you were able to gain through creating something? How we have to develop it that way?
So let's say the increase of in productivity is about 40% for the work of the conceptual design. So it's quite a lot. And the second part was the whole question or another aspect?
No, that was all.
Okay.
But if you say 40% productivity, 2000 is much too cheap.
Yeah, that's also what I think.
Yeah, okay. So we are right now on the marketing and speak a lot with the marketeers. The whole point is that you have to get into a settled market, the magic market. And if you are too expensive, you have a lot of one-man engineers around. If you sell it for 5,000, it's too expensive. So the strategy, the marketing strategy, is that we start with a low price, and then you can update to higher versions in order to get more functionality. But I feel the same. But yeah, a lot of stuff. Like, do you know Rhino, for instance? It's very popular in architectural design for NERP design. It costs 900 euros. Yeah, so it's the price is dictated by others.
Last question.
You mentioned the OpenGL was a problem, and you had to go to native C. Can you tell me, was that because of like matrix calculations and vector calculations in Common Lisp, or was the calling out to the OpenGL API was too much of an overhead?
So I'm not completely familiar with that detail, but the point is that in France you have an OpenGL API, and the whole drawing of the geometry just took too long. And so now we are reusing in C, we're using a tree where we remember which elements haven't changed. So we just redraw parts of the tree and not the whole building. And this is not really, as far as I know, possible simply in this Franz API functionality.
Okay, so you're using some sort of tree software. I don't think that comes with OpenGL, right?
No. It's developed by ourselves.
Oh, right.
It's a 3D decomposition idea. This developed by a guy who did his master thesis on that topic in our company.
Thanks a lot. 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 Thanks a lot.